Okay, so I'm going to be working on chapter 12, part 2. So let me go ahead and share my screen. Actually, I'll do this one right here. Now click on this. Okay, we're looking at the conductivity of solutions. So we're being told here, in order for a solution to conduct electricity, there has to be a certain criteria that has to be fulfilled or met. So the question is, what criteria must be fulfilled for a solution to conduct electricity? That's the question we're trying to answer. We are told for electrical current to flow and light the bulb, the liquid in which electrodes are immersed must contain ions. So the requirement here, or the prerequisite, is you have to have ions inside the liquid. And these ions are able to carry electrical charge, okay? So we're told, we're actually, if you look at this right here, comparing 3 different solutions. The first one is pure water, so just H2O. Second one is table sugar. So table sugar here represents molecular compounds, okay? If you're gonna group these, molecular compounds. Water represents a neutral compound that is neither molecular. Well, I guess you can technically classify water as molecular, but water is mostly classified as neutral, okay? So you have molecular compounds. These are made of nonmetals. And then you have table salt here representing ionic compounds. Remember, ionic compounds, these are made up of metals plus nonmetals, okay? So in general, when ionic compounds are in solution, when they are dissolved in water, they tend to conduct electricity. That's the bottom line rule, okay? So when ionic compounds are dissolved in water, what do we see? They conduct electricity. Okay. So if these solutions conduct electricity, they must be fulfilling that prerequisite, which is they must contain ions. Let's see. We're told here pure water does not contain ions. That's a requirement, right? And thus does not light the bulb. Must have ions to conduct electricity. This is the requirement. And apparently water, pure water, does not meet that requirement. And therefore, as we can see here, there is no light, okay? No lighting of that bulb. Next, the solution of sucrose, this is table sugar and pure water, also lacks ions. Once again, the requirement we see here is must have ions. Does the sugar water solution have ions? No. And because of that, it fails to light the bulb. You look at the bulb again, no light. Well, if you look at this last one here, you can see there is light, right? You're able to light the bulb. If you're able to light the bulb, guess what? You're able to make a solution that contains ions. The solution of sodium chloride and pure water contains ions and thus lights the bulb, okay? Remember, ionic compounds are made up of oppositely charged ions attracting each other. In sodium chloride, you have sodium, the positive ion, that is drawn to chlorine, the negative ion, okay? Now, the explanation here gets a little bit more detailed and more technical, but I'm gonna keep it at that simple, straightforward level, okay? As these are trying to attract each other because opposites attract, there's an exchange of charge. And as long as you have charges, charges can carry current. For that reason, they carry electrical charge. For that reason, they can transfer electricity in the solution. Moving on, now we're talking about Lewis diagrams. Lewis diagrams is very important in the next couple of chapters. You see Lewis diagrams in chapter, actually, no, it's this chapter and the next chapter, right? Chapter 12 and 13, where we talk about how to draw Lewis structures, okay? What is Lewis diagram? Lewis is a scientist who worked in so many different areas of chemistry. One of the major areas he's known for is drawing the Lewis diagram, where he shows how elements combine together using their valence electrons to form compounds. From the Lewis diagram, we're able to see how elements connect with each other. So we're told It's essentially an electron dot symbol that is used to show the bonding arrangement between atoms in a molecule. So remember, the atoms are the building blocks that make up a formula or compound, okay? Now, what Lewis does is Lewis loves dots. Lewis uses dots to illustrate or to show bonding. So his claim to fame is that he did a very good job at introducing us to how elements bond and why they bond the way they bond. So our first example that we're seeing here is, so in nature, you will see fluorine, the element, existing as diatomic molecules. So why is that the case? Let me go ahead and add a page here. It's been a while, y'all. I'm a little rusty on this, but together, when I say together, I mean, I'm trying to encourage myself. We'll figure it out, okay? So right here, we got F2 down here. The question here is, why does fluorine exist as a diatomic molecule? Okay. In nature, when you see fluorine, why don't you just see a fluorine atom? Why do you see fluorine molecule, F2? So the question here we're asking is, why F2, not F? This is the question we're about to answer. Well, scientists notice that certain elements have an affinity. They have this unseen attraction towards each other. So one atom of fluorine has an attraction towards another atom of fluorine that makes them combine together when they're single. And when I'm saying single, I mean they're not in a compound, right? As long as you have two uncombined fluorine atoms in nature, they will bond to each other and exist as F2 until they're ready to combine with other elements. Then they have no need for each other. They break up and then go and combine with other elements. So they're always diatomic when they're single, and when they're about to couple or get together with other elements, they break apart, okay? So it's a relationship of convenience. So how do they join together to get F2? You want to start by drawing the Lewis symbol for each element, okay? So in this case, each fluorine, because we're trying to show how two fluorines get together, right? And to draw the Lewis symbol for each element, what you need is the number of dots. And the dots here equal group number or equal to valence electrons. So what Lewis does here is he also introduced the idea of a Lewis symbol for the element, which is essentially the element symbol surrounded by the dots, and those dots are equal to the group number or the valence electrons, okay? So let me see. Once again, I have to kind of reintroduce myself to using this app because it's been a while. Okay, fluorine is in group 7, right? So each fluorine is surrounded by 7 dots. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, fluorine elements do not like to exist as individual atoms. They would rather pair up for stability. That way, each fluorine, even as a single atom, when it's not in a combined form in a compound, will be surrounded by 8 electrons. So what they do to achieve that state is these fluorine atoms will share unpaired electrons. So we see right here, share unpaired electrons to form bonds, okay? That's their plan for combination. So we see right here that each fluorine combines. So this line here now represents the shared electron. And what I like to say is when you're looking at elements participating in a covalent bond, it's essentially like someone getting in a relationship, right? And they got some money. And the money here represents or symbolizes electrons. So there's money that they're going to put into the relationship. That's the bond, shared electron. And then there's money that they'll keep for themselves on this side. These are the lone pair electrons. These lone pair electrons only belong to the individual element they came from originally. So to illustrate that, these three sets of lone pair electrons only belong to the fluorine on the right. The fluorine on the left does not have access to those three sets of lone pair electrons. And then using a different color here, these lone pair electrons here belong to the fluorine on the left. The fluorine on the left does not share those three sets of lone pair electrons with the one on the right. That's why they're called lone, because they only have one fluorine element's name on them. Okay, so these are lone pair electrons. And right here, we have lone pair electrons belonging to only one element. Ergo lone, one alone, okay? That's kind of how I viewed it when I was going to school. I was like, okay, the terminology kind of explains what's going on. Okay, so in covalent bonds, we're told here, just like we saw, unshared or unpaired. So it's unshared or unpaired. They have to be single. So single electrons. Sorry. This is something else. Okay, sorry. Unshared electrons after the bond is made, right? So they're talking about something else. Sorry. I jumped ahead. I thought they're going somewhere else with this. The unshared electron pairs are also called lone pairs. And I already went ahead and explained that right here, right? These are the ones that belong to one element by itself, ergo alone, lone pair. Okay, the octet rule is a rule that scientists came up with. It's a generalization, right? Scientists, especially chemists, like to study trends because a lot of things that we see in chemistry is very trendy, right? We tend to see patterns and we see them all the time. And we recognize these patterns over and over again. When we start to see a pattern over and over again, to help us get to that pattern quicker and recognize the new situation, we come up with rules or hypotheses. So the octet rule was that rule that was coined or put together when scientists noticed certain behavior in elements. So what does this rule say? It says, in general, so of course, with every rule in chemistry, you have an exception, right? In general, atoms tend to form stable bonds by sharing or transferring electrons until the atom is surrounded by a total of 8 electrons, okay? Let's try to break this rule down so we can see what's being communicated here. So this is kind of how I look at it, right? When I was learning this, at first I was so afraid of chemistry. Then I moved on to the point where I was like, okay, you know what? Let me try to see the elements like they were people I was trying to get to know. So these elements, in the form of atoms, they have an agenda. What is their agenda? According to this, the agenda is stated right here. They have a goal, and the goal here is to be surrounded by 8 electrons, okay? So agenda, to be surrounded by 8 electrons. 8 electrons is also called octet. Okay, that's their goal, that's the agenda. Okay, how do they achieve their goal? We're told here. They achieve their goals by forming bonds. And how do they form these bonds? So goal achieved, I can't spell, by forming bonds, okay? And the question is how? They either share, lose, or gain electrons. Okay, so when you look at it in that suspicious kind of way, or you look at it as the elements are doing what they're doing because they're actually trying to get something out of this relationship, then you can see, oh, okay, now I see why they're doing what they're doing. Atoms have an agenda. They want to be surrounded by 8 electrons. So you're probably asking, right? If you're like me back in the days, first I had no idea what the teacher was saying. And then when I did, then I had all these new set of questions. First of all, it was like, what are you talking about? Why is 8 so important? Okay, in the world of elements, 8 is stability. It's a symbol of stability. You know when you've made it in life? When the elements have reached stability, that is symbolized by being surrounded by 8 electrons. So when they're striving to form bonds with each other, bonds with other elements, they're really trying to reach that status of stability, right? That status symbol, stability, octet, 8 electrons. Okay, then we're moving on to polar and non-polar covalent bonds. So the context of this is covalent bonds. Now, I'm recording this lecture a couple of years after recording the first part. So something happened with my recording to where the original source of the recording got archived by admin. Okay, I had no control over this. So then you don't have access to the link anymore, and I have to re-record. So I don't remember what I said. Bottom line though, covalent bonds, real quick, covalent bonds are formed when elements share electrons, okay? So I'm going to take a step back and talk about the context. Okay. Covalent bonds, the context here is, of course, they're bonds, right? These are formed by sharing electrons. Okay, so going back to this right here, we're told there's such a thing as polar and non-polar covalent bonds. So let me start with non-polar. Non-polar covalent bonds. So here's the thing I want to say about terminology in chemistry. Terminology is key. Oh my goodness, I can't say this enough. I went out with my friend recently. She's another chemistry professor. And as her and I were having dinner, we're talking, we're learning something new in our lives. It has to do with the financial world. She's saying, remember how in chemistry terminology is very important? I'm like, yes, terminology is key. It's very important to know what the words mean. And it's very important to know what the context is, right? So non-polar here means, well, I'm going to paraphrase, right? Not different. This is my layman way of saying it, not different. This is no difference, right? So let's see other areas where the term polar has been used that we're probably more familiar with. This is Christmas time, by the way. Merry Christmas. It'll be Christmas in a couple of days. And we know Santa comes from the North Pole, right? I know he's a fictional character, but he's in the North. Y'all know North Pole, right? So we at least know about North Pole and South Pole. And the idea is these poles signify a difference. I don't know what the origin is, but anyway, a difference, right? North and South. Okay, so at least there's a polar express, all that stuff. Polar just means different, okay? What other area do we know? Oh yeah, topics, right? We're in a season of COVID. You might be hearing this years later after COVID is over. I'm just imagining that right now. But anyway, we're in a year of COVID where the whole thing about COVID, vaccines and stuff, the news says it's very polarizing. What do they mean? What does polarizing mean in that context? Polarizing in that context means it's a topic that divides people, divides them into different groups. Once again, the word polar being used in the context of difference, okay? When you say someone is, you're kind of acting bipolar, you're meaning that the person is acting like two different people, right? All those examples I have given you, polarizing, North Pole, South Pole, bipolar, is all communicating different, right? So when we say something is non-polar, we're saying it is together, not different. Not the word polar itself. Polar just means different. Non-polar just means non-different. They could have said it better. I agree if you're thinking that way. This is how they chose to say it. Non-polar, not different, okay? So once you draw the lowest structure, you will see some bonds where there is not different. Okay, so back to covalent bonds, back to the definition. Non-polar covalent bond shows elements sharing electrons equally. Okay, so I did all this just to define what nonpolar was, right? And then to tell you that in a nonpolar covalent bond, the elements sharing the electrons share it equally, and the opposite of equally is not equal. Okay, so the example here will be like when two fluorines are forming a bond like we saw earlier, the bond formed here is nonpolar. Why? Because both fluorine have the same level of access to the shared electrons. Okay, so I'm going to try to paraphrase that here. Both fluorines have equal access to shared electrons. Now, I'm trying to go as detailed as possible because when I took this class, our curriculum was different. So it was kind of like in middle school. The way I was hearing this was a whole different level. And it made it harder for me to answer questions because I didn't realize there was depth to what was being said. I thought it was just superficial, like they're sharing electrons. It's not that simple. The way they share can be very different. Okay. So to illustrate an equal sharing, I'm going to use a custody battle because that I feel like that really explains the unequal sharing. When you have polar covalent bond, this is the opposite of nonpolar covalent bond. Here you have a bond formed between atoms or elements, same thing, where electrons are unequally shared. Okay, so once again, to really, I feel like bring the point home, they're sharing, okay? In the eyes of the law, in the eyes of the world of chemistry, they're still sharing, but they're just not sharing equally. For some reason, one of the elements, and the reason is electronegativity, okay? One of the element has certain access or privilege that allows them to just have more access to the shared electron. So to illustrate that, I'm going to give you guys an example of hydrogen and fluorine, okay? We'll learn down the road that fluorine is the most electronegative element. Well, as the most electronegative element, fluorine then has this special access to the shared electrons. Yeah, the electrons are being shared, but the electrons spend more time, like weekdays and weekends with fluorine. I mean, there's no time limit here, but you know what I'm saying. If these used to be, if these are a married couple and they're not divorced, they're not broken up, bond is still there, just separated, then the shared electrons spend more custody, more time with fluorine. Okay, so you see right here. Now they're talking about the shared electrons, not the lone pair electrons. These ones right here, they spend more time with the fluorine. Okay, so there's so many different explanations. The other way of looking at the same point here is to see that hydrogen as an atom is large and fluorine as an atom is really small, right? So let me actually draw this close to the hydrogen. So when they're sharing electrons, here's fluorine right here. The shared electrons occupy the space where the orbitals overlap. You see how those circles overlap? That's where the shared electrons go. Then fluorine electrons are here, 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 and these lone pair electrons belong only to fluorine. You can see because the fluorine is very small in size, the shared electrons are a lot closer to the center or the core of fluorine. So, I mean, some people want to argue that fluorine is not just selfish, keeping the shared electrons to itself. It's just that its size is very small. So the shared electrons spend more time near the center of fluorine, okay? On the other hand, the center of hydrogen is very far from the shared electrons, and the shared electrons don't spend that much time near the center or the core, the nucleus of hydrogen, okay? So some people say the size of fluorine makes it more electronegative. And I know I haven't defined this in this context yet, okay? So let me go ahead and define it, just get out of the way. What is electronegativity? What does this word mean? I remember learning this thinking, how rude. Electronegativity, this is the ability of an atom to attract, if I can spell, I want to say, yeah, to attract shared electrons to itself, okay? And the smallest atoms are able to do that the most. Now, I guess if you want to dig deeper, you're like curious to know, well, what makes it do that? The size of the atom, okay, number one. The other one has to do with where the shared electrons are compared to the nucleus, which is pretty much the same thing, right? The size of the atom. So there's something called the nuclear charge, which is the attractive force in the nucleus. I'm going too deeper than I wanted to go. Anyway, if you do want to know more, take the general chemistry class where I can go a little deeper, okay? I do get a little excited about this and then I go off. So let me just stay with this. Yeah, the size of fluorine is sufficient enough to explain why fluorine is very electronegative. Fluorine is the smallest atom of all the ones that we look at. And so it's the most electronegative. Okay, so here we're seeing a representation of the different kinds of sharing. You can see here, right? You can see right here that this is funny because in this picture shows the opposite of what I expected, right? Over here, I'm showing you the atomic size right there. What they're showing here is very different from the atomic size. They're actually showing you something completely different. Over here, they're showing you a non-polar covalent bond, and they're showing you equal sharing of bonding pair. So to illustrate that, they picked a generic element called X. We don't really have one called X. We have Xe, but not X. Some generic element. And this generic element combines with itself, and we can see here the shared electron spend. They're about equidistant, right? They're equal distance from the nucleus of this atom here and this one here, okay? So these electrons are equally shared if you're trying to figure out how far they are from each element's nucleus. On this one here, we can see these are unequally shared. Now on this one, on this picture here, they didn't really explain what was what, but we can see here the polar covalent bond and equal sharing of bonding pair. The bonded electrons here, you have the element on the left, that's X, the element on the right, that's Y. And you can see from this picture here, the shared electrons are a lot closer to X. But now mind you, they haven't defined what is what, right? So the shared electrons are a lot closer to X than they are to Y, right? Then over here, we have quite a different picture. In this one here, in this picture here, we don't have the same combination. We don't have X and Y. This is a different combination completely. We have M and X. In this case here, they're actually showing you the ionic bonding transfer of electrons. So in this situation here, M actually represents a metal, and this metal already lost electrons. And then X represents a nonmetal, and the nonmetal took electrons. So to really explain this one here, I have to take a step back and then bring it to this picture. So in this picture here, originally, the metal was large, the nonmetal was small. Okay, so I'm going to put it on the side here. The metal was large, nonmetal was small. Okay. The nonmetal is actually the more electronegative one, right? And so when they try to, in this case here, when they try to form a bond, the nonmetal pulls the electron from the metal, taking the extra electron, one of the valence electrons, to itself. In doing so, it grows bigger because it's gained electrons. And essentially, the body of the atom is mostly electrons. Bigger size, more electrons. Smaller size, petite atom, less electrons. So you see what happened here is after X got the 1 electron from M, it just got bigger. Since M has shed a little bit of electrons, it's now a lot leaner, a lot smaller. And that's what we're seeing here. So in this case here, the unequal sharing of the electrons was so bad that X took the electrons away from M, and they are not sharing again. They're not sharing at all at this point. But here's the thing, right? They're saying ionic bonding. Bonding means together. Well, how are you together when you're not sharing? Well, X took the electron from here. M is missing an electron, that's why it's positive. So how do they get together? They can't help it. Even though X took from M, what they got was opposite charges. So the opposite charge here makes them attracted to each other. It's not a toxic relationship, y'all. Believe me. No, it's not. It's like they took something from me, yet I'm so drawn to them. No, it's not. No, it's not. Okay. So X took an electron from M. The non-metal took the electron from the metal, right? That's what happens in the ionic bond. But what makes them come together, even after that transaction, is the fact that they have opposite charges. And then they're drawn together. And that's what causes the bonding. In these first two, it's the sharing of electrons. So remember over here, you're sharing electrons. In this last one here, it's not sharing of electrons that brings them together. They actually don't share electrons. There's a transfer of electrons from the metal to the non-metal. And then after the transfer takes place, then they have opposite charges and they're drawn to each other, okay? I already explained electronegativity. We saw that behavior in fluorine. Fluorine is the most electronegative element. I already mentioned that, check. The ability of an atom of that element in a molecule to attract bonding electrons to itself. So now if the atom is attracting its own electrons to itself, that's just being a small atom. But when you're attracting that which is supposed to be shared, that's just electronegative, right? Because it's like you're supposed to be sharing, but you're not. So one of the things you have to be able to do is identify what elements are very electronegative, what are least electronegative. So we're told here, fluorine is the most electronegative. So what you can do here when you're giving the kind of comparison question, remember, in this mock oversimplified, I get it, periodic table, fluorine is in the top right, okay? I skipped over the first energy level, that's somewhere up here, you know. Fluorine is in the top right, somewhere here. Oh, this is supposed to be over here. You know what I mean? This is noble gas right there. Fluorine is in the top right. What we see right here is as you're going towards fluorine from left to right, you have increasing electronegativity. If I can spell that right. So electronegativity is greater at the top of any column for main group elements. And electronegativity increases from left to right across any row of the table. So if you're going from top to bottom, you're going towards fluorine, electronegativity increases. If you're going towards fluorine from left to right, it also increases, right? From top to bottom, it gets bigger. From left to right, it gets bigger. As long as you're going towards fluorine, it gets bigger, okay? Okay, over here, periodic trends, electronegativity values. Let's see, what do we have here? Oh, I essentially explained that. Remember, going towards fluorine, it gets larger. And there are some questions that you'll be asked where you're supposed to provide or use these numbers. You want to use these numbers right here. And let me show you a neat way to remember period 2. We don't use period 1 that much. Well, we use hydrogen, I would say the most of period 1 to figure out electronegativity between hydrogen and carbon and things like that. But if you want to remember the trend in period 2 for whatever reason, fluorine is the highest at 4.0. So what I'm going to show you here, period 2 has the following elements. I'm going to copy these. Sodium, magnesium, and then right here, boron. No, sorry, I went the lower. lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So we're going backwards, right? You start by assigning fluorine 4.0, and then let's see, from fluorine to, I feel like my eyes are just kind of all over the place. I'm struggling to see this. From fluorine to oxygen is 3.4. So you can see the gap between these two is what, like 0.6. From this to nitrogen is 3.0. And the gap here is what, 0.4. From nitrogen to carbon is 2.6. The gap here is what, 0.4. From carbon to boron is 2.0, gap is 0.6. From boron to beryllium is 1.6, and the gap here is 0.4. And then from beryllium to lithium is 1.0, and the gap is 0.6. So the gap kind of fluctuates between 0.6 and 0.4, right? So we got 0.6 here, here we got 0.4, here we got 0.4, here we got 0.6, 0.4. Oh, sorry, I misread that. Why did I misread that? My astigmatism. This is what I get for not really, because I'm looking at that saying something's kind of off here. You know what? I think I didn't mess up there. No, I did read the right place. When I looked up, I read the wrong place. Yeah, so 0.4 and then 0.6. It fluctuates between 0.6 and 0.4, right? But essentially, that's one way of looking at this. For you guys' level, though, they won't really ask you to memorize this. So just kind of give you the numbers. So that makes it so much easier, right? But if you're taking a majors class, you would have to memorize this. They won't give you the numbers all the time. You want to be familiar. So how do we use these tables right here? They should give you a table. I don't see the table right here. They should give you a table that tells you what the electronegativity differences are and what they signify. So the electronegativity the gaps between the bonds, or the electronegativity value between the bonds, tells you what type of bond you have. If the change in electronegativity is equal to 0, then you have, let me make a brand new sheet of paper for that, because I feel like I need that, okay? Where is it? Okay. Change in electronegativity values, okay? And then types of bonds. Okay, so if the gap between the electronegativity values of two elements is, say, 0, so you're gonna actually find the difference and then figure out the absolute value of that, and I'll show you how to do that. If the difference is 0, the type of bond here is usually called pure covalent bond, okay? Sometimes it's called non-covalent bond, but the difference is from 0 to, hold on a second. For a moment there, let me just pause this for a second. Can I pause this sharing for a second? Let me see. How do I go to the...
Recording progress.
Okay, so let's see here. Back to this. This is 0, 0. Oops, wrong thing, 0.0. Then here I have 0.1 to 0.4, and this is called non-polar covalent. And then when you have a difference of 0.5 to 1.7, this is considered polar covalent. And then when you have a difference in the electronegativity of the elements, that's 1.7 or greater. I've seen some books that use 1.9, and this is called ionic, okay? So once again, you have to figure out the change or the difference in electronegativity values. And since all these numbers are positive, whatever number you get, you have to multiply. If it's negative, you have to make sure it's positive, okay? So to illustrate that, I think, yep, they gave you some examples here. So figuring out electronegativity differences, right? And this helps you get the polarity of the bond. Let me get some water. Okay, the polarity of a bond, which is something that you want to know how to figure out by calculating the difference between the electronegativity values for the bonded elements. So the bonded elements either have the same electronegativity or they have a different electronegativity. Whatever it is, you're going to subtract because it's by difference, right? You subtract the two values and then find the absolute value, which is if it's a negative number, multiply by -1 to get the positive value. So we use this symbol right here in math, right? The absolute value. Okay, so between H and O, we're going to be looking at H and O, H and C. Let me add one here, H and F. Is that all they gave you? H and O, H and C? And then let's say H and H. Okay, so I'm going to add a couple more right here. So we'll do H and O, H and C, H and F, H and H, okay? So I need the numbers that are in the periodic table. H is 2.2, so I'm going to take 2.2 minus 2.2 minus 2.2 minus 2.2. I'm finding the difference between the hydrogen atom's electronegativity and then the other atom the hydrogen is combined with, okay? First one here, hydrogen is combined with oxygen. Oxygen is what? 3.4, 3.4. I'm going to find the difference and then get the absolute value. Where's my calculator? Hold on. These things are all over the place. When I say these things, I mean my calculator. 2.2 minus 3.4. Oh, is it dark in here? I feel like it's dark. Okay, hold on. 2.2 minus 3.4. Okay, I technically get a -1.2, but we take, oops, sorry, slippy hands. Take the absolute value 1.2, okay? The positive value of it. Okay, same thing over here. 2.2, and what is carbon? Carbon is 2.6. I hope I'm reading this correctly. Yeah, 2.6, 2.6. So 2.2 minus 2.6. And the gap I get here is technically -1 or 0.4, but take the positive value, absolute value, 0.4. Then I have 2.2 minus fluorine is 4.0 right here. 2.2 minus 4.0, and I get 1.8. And then over here, I have, 2.2, and then hydrogen minus hydrogen itself, 2.2. I get 0, right? So I'm going to classify the bonds based on the electronegativity difference. So over here, if the difference is 0, like here, this is going to be pure covalent, as in pure sharing, perfect sharing, no animosity, pure covalent bond. That's the type of bond between two hydrogens. It's pure covalent, pure sharing. And then what's 1.8? 1.8 is actually, well, here it says 1.8 is ionic. So you can technically, depending on the book, some books will classify 1.8 as polar covalent, because I've seen somewhere this goes to 1.9. Okay, it's tricky. Scientists don't even agree with these categories. So I would say I have seen this as both polar covalent or ionic. And so I would say snap. The more common one, just to be fair, because you're already asking you just on the exam, or do I answer? The more common one I have seen for this is 1.9, which is, is the one where the 1.9 is still classified as polar covalent, okay? So the more common one I have seen out there in random books is polar covalent. Now, it's right on that border, so some people classify it whenever convenient as ionic. And here's a caveat. When HF is a gas, it acts more molecular, but when it's put in water, it acts more ionic. It's weakly ionic, but it's more ionic. So it's that molecule that's right on the border. I feel like I'm going deep again. I didn't mean to go deep, but just in case you're the kind of person who's like, well, which one is it? It's on the border. So some classifies as polar covalent, some ionic, okay? Point 4, this is a little bit more definitive, non-polar. So CH, even though it's different elements, the way they share electrons is not different enough to be classified as polar. So this is non-polar. And then OH will be classified as polar, right? Because OH falls in this region here. It's going to be polar. So we got polar, we got pure covalent. Or some people will classify this as ionic, okay? But just to be fair, I try not to give you on the exam things that are very ambiguous, because once again, this is a non-majors class. I don't want to give you something where we can be arguing about the answer, possibly, okay? Okay, we're close to the end of this section, this chapter here. How am I doing with time? Okay, not too bad. Then we have multiple bonds. We have single bonds, double bonds, triple bonds, and we're being told here these are different. Single bonds are formed by sharing of one pair of electrons by two bonded atoms. So you have the same atoms, not only sharing a pair of electrons, well, in this case, they're sharing a pair of electrons, right? In a double bond, the same atoms share a pair of electrons first, and they go back and share an additional pair of electrons in double bonds. And then triple bond in compounds or in atoms, you have the same atoms sharing three separate pairs of electrons. So they bond the first time, they bond the second time, and then they bond the third time, okay? So they should show us here how to make these multiple bonds. Oh, they do. Okay, great. Okay, so what I'm gonna do is show you real quick here. When hydrogen atoms form a bond, these hydrogen atoms, actually, just to be fair, let me stick with something that's more relevant. Let me stick with the octet, bonds that form octet. Like we mentioned earlier, fluorine in group 7, having 7 ampere, not 7 ampere electrons, but being surrounded by 7 electrons. Each fluorine then shares the unpaired electron to form the bond. This is considered single bonds, sharing of one pair of electrons between or by two bonded atoms. This is going to be single bond, okay? Maybe to be more specific, let me show 2 dots right here. Okay, next, double bonds. With the double bonds here, let me see what forms double bonds. Oxygen. Okay, let's see why 2 oxygens, I'm going to need some space here. Let's see why 2 oxygen atoms will form a double bond, okay? So the formula here is just F2. Here the formula is O2, but why do they form double bonds? Why does it take all that to obey the octet rule? Let's see. Each oxygen comes into this relationship with 6 electrons, right? Because oxygen is in group 6. So I got 4, 5, 6, 4, 5, 6, right? 6 on the right, 6 on the left. And you can see each oxygen currently has 2 unpaired electrons. Those unpaired electrons pair. So these pairs, I'm going to redraw them in such a way that they can pair with each other. Oops, I didn't mean to erase the whole oxygen, but y'all see this right here pairs with this right here. So these are paired together like that. And so these become the double bonds as they're shared. These are shared, these are shared, these are shared here. Okay, in N2, where we're going to be seeing triple bonds here, we see N and N. Each N is in group 5. So I have 1, 2, 3, 4. I guess I put it right here, 5. 1, 2, 3, 4, 5. Okay. Oh, one thing I failed to mention. My bad. I failed to mention this. Let me go back here. When we are done, I'm going to use colors to illustrate how the octet rule is being followed, right? The fluorine on the left currently has access to the following to help it get to octet. 2 electrons here, 2 here, 2 plus 2 is 4, plus 2 is 6, plus 2 is 8, okay? Remember, the electrons between the 2 fluorines are shared, so each atom has full custody of those shared electrons. I'm going to use a different color to illustrate the other fluorine, the green color. 1, 2, 3 times 2, that's 6, and then this. So essentially, the electrons in the middle are occupied, or I should say occupied, that's the wrong term. The electrons in the middle are owned by both fluorines on either side because they're shared electrons. Each fluorine has equal custody on those shared electrons. Over here, the oxygen on the left has the following electrons, right? It has, and this is how it gets to 8, how it gets to octet. 1, 2, 3, 4, 5, 6, 7, 8. With the green. Now I'm going to show the yellow, the one on the right. 1, 2, 3, 4, 5, 6, 7, 8. Remember, for each element to get to octet, it has to be surrounded by 8 electrons. I just showed you how each of them are surrounded by 8 electrons. They use the electrons that belong to themselves only, and then the electrons that are being shared. So it's a combo of all of those electrons. Okay. So right here, before I form the bonds, you can see, before the bonds are formed between the 2 nitrogen, each nitrogen has access to 5 electrons. That's not octet, right? To get to an octet, each nitrogen is needing 3 additional electrons. So they have 3 points of 3 electrons that are unpaired. Those 3 will connect, they'll be shared, and they'll be like that. And you can see how that becomes a triple bond, right? So this electron bond with that electron means going that way, well, that bonds with that, or that shared with that, with that. And so over here, let me see. Hopefully y'all see what people can see, right? So I'm going to show the shared electron in the middle of your CAC. Now you can see how each nitrogen achieves octet or gets to octet by the one on the right, 2 from here, 4, 6, 8, the one on the left. No. 2, 4, 6, 8. Okay. So yeah, if you're wondering, am I counting the shared electrons twice? Yes, because each element claims custody of those shared electrons. So when they're not being asked, when they're being checked for electrons, they count those shared electrons as their own. Okay. That's why those shared electrons are not called lone electrons. They're called bonded electrons as they're shared. Okay. This is triple bond. Okay. So over here, they're showing you other atoms that are bonded to 2 or more other atoms. Written differently. Maybe I'm just getting tired. I don't know. We'll see. So here they're showing you the formation of water molecule. Now, by the way, this process here is not using the elaborate Lewis steps. I'll show you that in the next chapter, right? The Lewis steps. So here we have formation of water molecule. On this one here, essentially, it's showing you how the water molecule is formed. So let me draw this on a separate page. This is not the Lewis's proper format. You know, I feel like I should just go ahead and show you guys that one because this one here is just unnecessarily confusing. If I don't do that one, I'll do that. I'll show you the other rule. Okay. In the other rule of drawing Lewis structures, it's a very elaborate step, right? Because you guys are going to be having your molecular geometry lab you're going to be working on. So for that one, rules for drawing Lewis structure. I think I should just show you this rule because I feel like it makes it so much easier. Okay, because right, this is a lot easier than the other rule, but in this rule here, in drawing Lewis structure, the first thing you have to do here, as it says in the rules, which you'll be seeing more in the next chapter, but I want to go ahead and show it to you right now, is to determine number of valence electrons. Okay, so actually let me pause this for a moment. Okay, so what I'm going to show you here is the simplified. I was going to show you the other way, but I decided to just show you the simplified rules for drawing Lewis structure. With this one, just like we did before, you want to go ahead and, I just realized the dot here. What's this dot for? Oh, interesting. Okay, so you start off with water, just like we did before. Draw the Lewis symbol. So Lewis symbol for each element. So I'm gonna kind of give you guys a process, even though it's not really shown here. You have hydrogen, and you have oxygen. So in a way, this is kind of like the one that's step by step, where you have to figure out what's in the middle. But draw the Lewis symbol. Remember, the Lewis symbol has the elemental symbol surrounded by dots, where the dots are equal to valence electrons. So remember, dots are equal to valence electrons. And the valence electrons are the same thing as the group number, right? Or group number. So I just realized I haven't seen the periodic table in a while. Where's the periodic table? I know I had it somewhere here. So this is, of course, group 1, 2, 3, 4, 5, 6, 7, 8. We're dealing with the A group, not with the B group, not this group right here. Okay, for water, I had hydrogen in group 1, and then oxygen. This is group 6, right? So where was I? Group 1 gets 1 dot, group 6 gets 6 dots. 1, 2, 3, 4, 5, 6. Okay. Number 2, pair unpaired electrons. Okay. Pair unpaired electrons. Let me find my unpaired electrons. These are unpaired. These are unpaired. And so we end up with oxygen up like that. And then the shared electrons are right here. Oops, not the right way to draw it. Dot. I'm trying to show you these are being shared, right? So these are going to be your bonded electrons, right? And then these ones in the middle are going to be your lone pair. They belong to oxygen alone. Lone pair electrons, okay? Yep. Oh, next one, NH3. Let me work on NH3 so you can see that. NH3. With NH3, right here, you got N, you got H, you got H, you got H. Okay, so you're probably asking me, if the formula is NH3, how do I know what goes in the middle? They will define this in the next chapter, but I'm going to go ahead and tell you right now. Usually the first element goes in the middle, especially if you have one of that element. How do I know I have one? You see how there's nothing written down here? The 1 is implied. And then this one here has a 3 in front of it. This just tells you that there's 3 hydrogens. The subscript represents the number of atoms that were just written, the number of atoms before it. So you have 3 hydrogens. There's 3 hydrogens, 3 hydrogens. And here the nothing usually means there is 1 and then there's 1 nitrogen, okay? Yeah, so 3 hydrogens, 1 nitrogen. Okay, back to the symbol. Looking at the Lewis symbol, let me go back to the periodic table. Where is nitrogen? Right here, group 5. So nitrogen will be surrounded by 5 dots. Let me see right here. Oops. 1, 2, 3, 4, 5. 5 dots for nitrogen. Each hydrogen has got 1 dot right there. Connect the unpaired dots, right? Connect this to that, connect that to that, connect this to that. Ta-da. We got our molecule. N, H, H, H dot dot. Okay, so you can see that the nitrogen in the middle is surrounded by 8 electrons, right? 2 here, 2 here, 2 here, 2 here. One bond equal 2 electrons. I hope you can see that, right? Okay, what else? Did I cover this pretty much? Yes, right there, done. Moving on to, exceptions to the octet rule. Okay, so apparently there are certain elements that tend to obey the octet rule and some that don't. Remember, the octet rule is a desire to get to that octet status, right? To live that octet life. Trying to be relevant. I'm just kidding, y'all. Just kidding. Okay, so carbon, nitrogen, oxygen, and fluorine, these obey the octet rule. Okay, they tend to be known for obeying the octet rule. So we want to be aware of the elements that are known to try to not obey the octet rule. And these are called the elements that have an exception to the octet rule. So here's the thing, right? When I was a student, as I said, I tell the story over and over again. I went from like, I don't get this at all. I'm never going to get this, the attitude, to wait, I'm beginning to get this. And this story is suspicious because I'm like, wait a minute. I started to realize the trend, right? I was listening, I was paying attention. I'm like, she's going to say this. He's going to say this. He's going to say this again. I've heard this before. All of a sudden, I'm realizing the rules they gave us always had exceptions. So I'm like, wait a minute. Do all the rules have exceptions? Easy answer, yeah. All the rules have exceptions because remember, the rules are generalizations that the scientists make about the elements. They study quite a few elements and they go, oh, I bet all metals do this. And they realize, oh, all metals don't do this? Exception to the rule. This metal behaves differently because it's an exception, right? So all the rules have exceptions. Anyway, here, exceptions to the octet rules. These elements, when you see this combination here or these type of elements, they will not follow the octet rule. Example, odd electron molecules. So when we start working on the valence electron, the Lewis structure rules, and you try to find the total valence electrons, which we'll talk about in the next chapter, okay? If you end up with odd number of electrons, this means whatever molecule you're building will never, ever obey the octet rule because the minimum requirement for obeying the octet rule is you have to be working with a total of even number of electrons, okay? So if you've been paying attention, you're probably saying, wait a minute, didn't nitrogen have an odd number of electrons? Let's go back there and see. Nitrogen had 5 electrons and each hydrogen did have 1 electron, true. But we had 3 hydrogens. So the hydrogens together had 3 electrons. This is odd and this is odd. But in the whole molecule, when you add them all together, what do you get? 8, and 8 is an even number. See how they get you? Yeah. So what you're dealing with is the total number of electrons from each of the elements in the compound have to add up to give you even number. If you add up and you get odd number of electrons, then that will not obey the octet rule. So the example we have here is NO, as in no, okay? Nitrogen has 5 electrons, oxygen has 6 electrons. When you add them, you get a total of what? 11 electrons. Total electrons in that molecule is 11. It's an odd number. There is no way possible this element can obey the octet rule. What about NO2? Okay, let's see over here. Each nitrogen has 5 electrons. Each oxygen has got 6 electrons. 6 plus 6 makes 12. When you add these two, what you get? 17. So no matter what, NO2 will not obey the octet rule. Does the molecule NO2 exist? Yes, it does. Does the molecule NO exist? Yes, it does. So how do we explain that? We just say that the way they exist doesn't obey the octet rule. Just because a molecule exists doesn't mean it's obeying the octet rule. It was just that the rule came about because most molecules obey the octet rules, not all molecules, okay? So they're able to remain, well, these molecules are stable-ish, okay? Most compounds that have one electron unpaired somewhere in the molecule or in the structure, they tend to be very reactive because they're trying to still find a pair for that unpaired electron. So you will look, when you see things like molecules with unpaired electrons, these usually have names like radicals. What do they have to be radical about? They have an unpaired electron they're trying to pair, right? So if you hear about radicals, where do we know about radicals in life outside of the lab? Aging. Radicals cause aging. Radicals also cause cancer and different illnesses. So if somehow a molecule is made and it has an unpaired electrons, many times it will generate a radical, and a radical is a very reactive molecule that is still trying, it hasn't given up, trying to pair that unpaired electron, just FYI. Yo, I love telling stories about these molecules. I feel like I know them, right? So you have those with odd numbers. And then the other one that they haven't, they do mention here, okay? The elements where you just have so many elements in the molecule such that, I don't want to say the only way, but the best way for the elements to combine to form a compound is by making so many bonds, okay? So let me draw this one here using the simplified format that I showed you guys, okay? So we're going to be looking at PF5SF6. PF5SF6, okay? Okay, so PF5, remember P phosphorus is in group 5, is somewhere here. Where's the periodic table? Oh, the periodic table is in the bottom, my bad. The periodic table is somewhere here on the bottom. P is in group 5, right? F is in group 7, so let's look at this. So P, because we only have one P will be in the middle. It's surrounded by 5 electrons, 1, 2, 3, 4, 5. And then F, each F is surrounded by 7 electrons, okay? So I'm going to draw the F, one F like that, 1, 2, 3, 4, 5, 6, 7. You can see here, fluorine already has 7 electrons. It's only 1 electron away from getting the octet status, right? So it really just needs 1 electron from here to be paired. So what I'm going to do so we can see the difference here is I'm going to draw the fluorine with blue color. 1, 2, 3, 4, 5, 6, 7. And it gets this 8th electron from phosphorus. Next fluorine, 1, 2, 3, 4, 5, 6, 7. Oops, 7. Once again, that fluorine gets its 8th electron from phosphorus. Over here, 1, 2, 3, 4, 5, 6, 7. That fluorine gets its 8th electron from phosphorus. Over here, 1, 2, 3, 4, 5, 6, 7. That fluorine gets its 8th electron from phosphorus. Over here, 1, 2, 3, 4, 5, 6, 7. Okay, so the multicolored electrons, these are shared electrons. These are the bonds. So if I was to draw this out, I'll just make this P, 1, 2, 3, 4, 5, F, 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 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yep. And this is PF5. Okay. So we're talking about molecules with more than 4 electron pairs surrounding the central atom. In this case here, okay, each fluorine is surrounded by 8 electrons, right? If you look at the fluorine, it has 6 dots, okay? And these 6 dots make 3 lone pairs of electrons. And then it has 1 line, and the 1 line makes 1 bond. And essentially 3 lone pairs and 1 bond, these make 8 electrons. So the fluorine is surrounded by 8 electrons, but what about the phosphorus? The phosphorus has 2 here, 2 here, 2 here, 2 here, 2 here. This phosphorus is surrounded by 10 electrons. Isn't the goal to be at 8 electrons? Yeah. This phosphorus has to accommodate more electrons than 8 in order for this compound to exist, because if it can't do that, where will the fifth fluorine go? It has nowhere to go. So the central atom that is selected to form the bond has to have that capacity, the ability to expand its octet to host all the surrounding elements, okay? I see the central atom as a host. Okay, what's happening over here? Back to the red. Sulfur, like before, 1, 2, 3, 4, 5, 6, okay? I'm gonna shortcut this process now and put the fluorine here. 1, 2, 3, 4, 5, 6, 7. The fluorine here, 1, 2, 3, 4, 5, 6, 7. The fluorine here, 1, 2, 3, 4, 5, 6, 7. The fluorine here, 1, 2, 3, 4, 5, 6, 7. The fluorine here, 1, 2, 3, 4, 5, 6, 7. Final fluorine here, 1, 2, 3, 4, 5, 6, 7. Okay, and each of these then become a bond, a bond, a bond, a bond, a bond, a bond. So you can see, as usual, the fluorine is surrounded by 8 electrons around each fluorine, 6 dots, and then the one bond counts as 2 electrons. But what about the sulfur, y'all? What about the sulfur? Sulfur is surrounded by 12 electrons. Now, why would sulfur go ahead and do that? Because sulfur has to be the host. It's the central atom that is taking care of and bonding to keep all of these surrounding atoms present, right? And it does so, it has to hold on to 6 fluorines. And to do so, it has to be surrounded by 12 electrons. That is 4 beyond the octet, right? So these are called expanded octet, more than 8. Okay. What about these ones here that have less than? I mean, there's a standard, there's exceeding the standard, expanded octet, and there is not even meeting the standard. What do we do here? Okay. So with this case here, these elements just showed up with not enough electrons, okay? So let me go ahead and add a page here. I didn't think this lecture was going to be this long. I don't know. I'm just a talker, I guess. BeF2, BE. What they use for this other one? Was it F also? Oh, this F is getting a lot of, hold on. BF3. Okay, once again, so BE is in group 2. So BE has 2 dots. And then F, like we've seen so many times, F is in group 7, so it has 7 dots. So this is the 7th, right? Or let's say the first, 2, 3, 4, 5, 6, 7. Then the other one, first, 2, 3, 4, 5, 6, 7. There. So you can see these form the bonded electrons, BE, F, F. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. And then let's see. Let's start with blue in the middle again. This time we got B. Boron is in group 3. So we got 3 dots. 1, 2, 3. And then fluorine is in group 7. So we got 7 dots. 1, 2, 3, 4, 5, 6, 7. Fluorine. 1, 2, 3, 4, 5, 6, 7. The other fluorine. 1, 2, 3, 4, 5, 6, 7. Okay. So from here we have boron in the middle. These are the bonds, bond, 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 fluorine, 1, 2, 3, 4, 5, 6. Fluorine, 1, 2, 3, 4, 5, 6. Fluorine, 1, 2, 3, 4, 5, 6. You can see right here, going back to the amount of electrons or total number of electrons surrounding the central atom, you can see right here, boron is surrounded by 4 electrons. And then, beryllium, this is boron surrounded by 6 electrons, right? Beryllium 4 electrons, boron 6 electrons. And what's happening here is this is definitely less than octet. And when you find these elements in the compound, they don't multiple bonds to get to octet. They just find the way they are. How are they okay the way they are? They're able to, when you get to, if you choose to go the non-majors route, you actually find that the 4th space here that was not occupied by a bond later on scientists are able to make boron form that 4th bond because they're like, we know you haven't reached the level of octet. There is room for one more bond. So later on in the majors class in 1412, scientists are able to get this boron to accept that fourth bond. Because scientists like to do things like that. It's like, we know, we don't know, we know you're able to do this. So we're gonna push you until you do what we believe you're capable of doing. Yeah. In the majors class, we talk about that, okay? But these molecules form less than octets. So looking at the periodic table, how can we tell which molecules or which elements do not obey the octet? So let's start with the ones that do, right? This is a quick summary. The poster elements for octet, SNOF, that group right there, carbon, nitrogen, oxygen, fluorine. Those elements right there, octet all the way. What about the other ones that do not obey the octet? Right before SNOF, right? Elements, carbon is the first element that obeys octet. Before it, we have boron, we have beryllium, we have lithium, we have helium, we have hydrogen. All of these less than octet. They just don't start off with enough electrons. They start off with a deficient number of electrons to where it's difficult for them to get to octets. They just don't. It's like, we can't get to octets, so we don't, okay? Now, what about this one right here? If these elements here and below, okay, so we see phosphorus, sulfur, chlorine. If these and below, we're going down. If these are central atoms, they can have expanded octet, okay? So you want to be aware of that. The majors class, we tend to look at that more deeper, and then they have to memorize more, but you want to be aware that if the number on the right is like this one here, where you have 6, anything more than 4, like this, you have PF5 bigger than 4, SF6, this is going to be expanded octet. Okay, if it was CF4, this is just right at octet because you have 4 groups and they'll form 4 single bonds. But 5 and 6, that's way beyond octet. Okay, so that's the easiest way to tell at you guys' level from the formula alone what is octet and what's less than octet. Okay, we're close to the end. Yay. Okay, metallic bonds. Okay, so it's been a while since I talked about bonds because I started in the other chapter or in the other video. So in metallic bonds, we talked about ionic and molecular bonds before. Now we're talking about bonds that are formed between elements, in this case, metals that are both large. So you have a large metal attracting a large metal, and they're about to form a bond. And we know they form bonds because we have alloys, we have, elements that form metallic bonds. We see them out there. Well, alloys is something else. Actually, technically, alloy is a mixture, so I shouldn't have brought that up. We're talking about metallic bonds, okay? So let's stick with that, metallic bonds. Okay, with metallic bonds, what we see here is because both metals at the fundamental level are large atoms tend to, this is their behavior, their isms, right? Tend to lose electrons. That's why it's very common to find large atoms, opposites attract, paired with smaller atoms in the ionic bonds. But how do 2 large atoms get together and form a bond? Do they get together? Yeah, we see that here. How they get together? Do they change their nature? No, they both behave like large atoms. So each metal in the metallic bond gives up its electron. Why? That's what they do when they're large. So attractive forces between positively charged metal ions in a crystal and negatively charged valence electrons that move among them. So essentially, this is them before, okay? Let's assume these are group 1 metals, because this will make my analogy or my illustration very easy. If they're group 1 metals, each metal then loses its electron and it becomes smaller in charge because it has lost its electron. This one here loses its electron too, it becomes smaller in charge, it's lost its electron. Well, who gains the electron? Nobody. They just give up the electrons and then they form ions. Well, apparently the lost electrons are now attracted to the original. So you're not really gaining them to become neutral, they're just attracted to them, right? But they're not just attracted to their election that they gave up. They're attracted to all the elections around them. So there is this thing, I call it a socialist communist camp kind of vibe, that the electrons in the metallic bond are delocalized. So another chemistry term, delocalized. Delocalized is the opposite of local. Local is kind of contained in a fixed place. Delocalized is like diffuse, it's spread all over the place. So to kind of illustrate this very well, look at that. So here we're seeing these metal ions that have all lost electrons. These are group 1 metals. How do I know? Because the charge after losing electrons is +1. On the right side, we have group 2 metals. How do I know? It's +2 charge, right? 2 positives right here. And if you were to count, 1, 2, 3, 4, 5, 6, 7, 8 metal ions, 1, 2, 3, 4, 5, 6, 7, 8 electrons. The number of electrons have to match the metal ions because remember, each metal ion is losing 1 electron. Okay, so this metal ion here attracts all the electrons and they all attract the electrons and they all share the electrons. So why do we really care about what happens to the electrons? We care because the ability for these metals to be so generous and share the electrons is what gives metals that unique capability to allow them to actually, conduct electricity, okay? When these electrons that are released here flow together, they conduct electricity, okay? Same thing with these, conducting electricity. And different metals have different capabilities of conducting electricities. Why? Because they produce different number of electrons. Man, this story gets so sweet. Let me end this chapter. I'm getting too caught up. Okay, to delocalize electrons do not stay near any single atom or pair of atoms or metals. These electrons are kind of swimming around. So they call this the electron sea model. Like the metal ions are swimming in a sea of electrons, right? Oh, this is reminding me of the beach right now. Oh, why? I could have been on the beach. I can't even swim, y'all. Okay, so we're talking about, while we're here, we're talking about alloy. What's the alloy? Alloy is not really a compound though. Alloy is a mixture. It's a solid mixture of 2 or more elements that have macroscopic metallic properties. So once you have the metals, you do have alloys, but alloy is not a compound, y'all. It's just a mixture, okay? But anyway, I thought I should end here. You have the electron sea model showing you 2 different metals with different capabilities. One can give up more electrons in group 2. The other one can give up less electrons in group 1. Each metal gives up 1 electron, and the electrons are collectively owned by all the ions in that metal. Same thing with this here. These have more electrons, probably conduct more electricity. These have less electrons, probably not conducting as much because the electrical current movement has to do with the number of electrons present. And with that, we will finally end this chapter. So right here, I want to write here and here. Okay. Let me see. Stop.